This is the third lecture on linear harmonic oscillator. In the last class, we have arrived at the result that the normalized wave function describing the harmonic oscillator is this. Today I want to find out the recurrence relation. If we consider the Harmonic polynomial, the generating function for Harmonic differential equation is g of xt is equal to e to the power twice xt minus t square, and this is equal to summation over n is equal to 0 to infinity t to the power n h n x by factorial n. If we differentiate this expression with respect to t, we get a recurrence relation which gives us h of n plus 1 in terms of q. This is one q, and if we differentiate it with respect to x, we get the relation these are the two recurrence relations for Harmonic polynomial. Let me first check the relations. Now we can write this equation. This equation can be written as hn of q is equal to n factorial to the power half, not minus half, it is plus half. Then phi n of q times e to the power plus q square by 2. If we plug this into this equation, we get for the left hand side this is the LHS. On the right hand side, the first term is 2q, then root pi 2 to the power n factorial n sin of q, and for the last term we have minus 2n root pi 2 to the power n minus 1 factorial psi n minus 1 q e to the power plus q square by 2. First thing, if we consider all the terms, then this e to the power q square by 2 is always in all the three terms, so we can cancel. Secondly, root pi is there, we can cancel root pi, so the left hand side we write as n factorial on the right hand side. We write this as These two factor is there is 1 root 2 and 1 root 2 has been adjusted with this. When this we take these two within the square root, it makes it 2 to the power n plus 1, and this n, 1n is taken inside the square root, so it makes it factorial n, and this. Now if we find that 2 to the power n and 2 to the power n times factorial n is present all alone, so we cancel this, so we get n plus 1 within square root phi n plus 1 times q, and here we have root 2q phi n of q, and for the last term we have root n phi of n minus 1 of q. This is the relation. If we want to write this one, so that q phi n of q is 1 upon root 2. In quantum mechanics, we will be very careful in using bracket. Third bracket means commutator bracket, so we shall try to avoid third bracket as far as possible. So if we take this on the other side, it is plus so the recurrence relation involving Hermite polynomial, when is transferred into Hermite-Weber function, this is the recurrence relation. If you strictly abide by the quantum prescription, then Q is the operator Q. So we replace this relation by now we come to the second relation. For second relation, we have to differentiate the Hermite polynomial on the left hand side and the Hermite-Weber function on the right hand side. So this is h and q is this much. If we differentiate this relation, then we get h and q, that actually means ddq of h and q is of derivative. So this part remains unaltered. Then first thing, this is the derivative of this, so phi n prime of q, then this is derivative plus q phi n of q. So if we substitute this value, you see that there is root pi, we we are not writing these two factors because they are obvious and gets cancelled. So we write the other factor. On the left hand side, we will have 2 to the power n factorial times and on the right hand side we will have 2n 2 to the power n minus 1 factorial So as usual, this can be written as 2 is taken inside, so we can write is root 2n and then n factorial. So if we cancel this part, we will have phi n prime q plus q phi n of q is equal to root 2n If we replace this relation by the earlier one, a more simplification is obtained. We can write first is this term, and when this is taken on the other side, it is 1 upon root 2 root n So one term is this, and we are to adjust these two. The factor is, one factor is 2 to the power n from this, and another factor is root n by 2. If we take root n by 2 common, then it is simply 1. So we rewrite it as this is the second recurrence relation. So we write the second relation as this is actually ddq of phi n of q. Only note the change in sign. So these are the recurrence relations which are very helpful in calculating the matrix elements. We first calculate the matrix element corresponding to the operator Q. So we are actually calculating this quantity. Phi m star q operator and phi n q integrated over dq from minus infinity to plus infinity. In evaluating this part, we replace these by the first recurrence relation, and we will have integration phi m star q. Then for this we write 1 by root 2 dq, which can be written as 1 by root 2 is taken out, and so the first term is thus. And second term is, this is a scalar factor you note that this is a delta function, because from the orthogonality we know that this is delta m n minus 1. Similarly, this much is delta m n plus 1. So we write it as if we consider that we are provided with n, then what are the possible values of m? So the one possible value is, we have n minus 1 is equal to m, or m is equal to n plus 1. So one thing is this. In which case we have used that m is equal to n plus 1. The system is going one step up, so this is n by 2. So no, not delta. And the other relation is from minus infinity to plus infinity. Here we consider the second term. So m is equal to n plus 1, or this delta function, when we are considering this delta function, m is equal to n minus 1. So I have written it wrongly, it should be minus sign. And if we consider the second part, when this contributes, so this is n plus 1 star q What is the significance of this result? We see that for all other values of m, the matrix element is 0. That means that if we have a system in a state n, say n is equal to 5, and this is a stationary state. That means that if we do not disturb the system from outside, and so that the system has the particle is subjected to a quadratic potential, then the particle will lie in the n is equal to 5 state forever. This is the meaning of stationary state. But if we disturb the system externally, then the disturbance, or so to say the perturbation, can be expressed in the form of x and p's. This is the so the perturbation is an operator, and as per the assumption of quantum mechanics, it can be written as a combination of x and p's. That is, if the perturbation or the disturbance is proportional to q, then under this disturbance the particle may go one step up. So this is the one step up, or this is the 6 steps, or it may go one step down. This is the 4th state. This is the meaning. If the perturbation or the disturbance is proportional to the displacement, then the system may make a transition from one state to the just neighboring adjacent states. If it goes up by one state, we call it excitation. And this is called de-excitation. Physically, if we want to mean that in this case the system engulfs one photon of a energy h cross omega, so it makes a transition from n is equal to 5 to n is equal to 6. So an absorption of photon takes place, and in this state the system jumps from a higher state to a lower state, and a frequency and a photon of energy h cross omega will be emitted by the system. For the reason that will be discussed in the others in the next class, we call it single excitation, and this is also single de-excitation. I will continue this discussion for other matrix element, but before going to that, I want to introduce a shortcut notation, that is the Dirac's BraKet notation. I am going to introduce Dirac's BraKet notation. This is Dirac's BraKet notation. We know that harmonic oscillator wave function, if we say an expert of quantum mechanics that a harmonic oscillator is in a state n, then for him it is sufficient to give n. So he writes the wave function as this. This is equal to, is actually equal to it is sufficient to supply the quantum number only, and the rest of the thing is known to the user. Similarly, if we say that the particle is within a box of length 0 to L, for a particle in 1D box from 0 to A, for him simple n is that the point that I want to make clear, that if you are already aware of the system, then it is sufficient to specify the quantum numbers, then the rest of the thing is implied. So how to represent the orthogonality condition in this case or that case? We generally write orthogonality condition as psi m star argument psi n dx from all x is equal to delta mn. You see that for the larger wave function, this is a lengthy process of writing, but in Dirac notation we write mn is equal to delta mn. This actually we are writing m, then so two parallel vertical line is unnecessary, so both two line is replaced by one, and when this bracket is completed, when the integration over all the variables of all the space variables is implied, that is definite integral over all the space variable has been carried out. This is the meaning. Actually this is a column matrix. This is a column matrix because when we solve the Hamiltonian equation, we write this is equal to n. So this is the ket, which is called the ket n, is a column matrix. So this is ket, and it is a column matrix. And if we take the Hermitian conjugate of ket, we get bra, and this bra n is a row matrix. Sorry. So when we multiply a row matrix from the left and a column matrix on the right, we get a scalar. This is the scalar. On the other hand, if we multiply this, then it is a column and it is a row. So if we have the same dimension, so it will be a matrix, that is, it will be an operator. When m and n are same, this operator is called the projection operator. So coming back to the system BraKet notation. So what we get in BraKet notation, if we like to write the orthogonality of the Hermite-Weber function, in longhand it reads as in Dirac's notation it is m n simply. Now coming to this matrix element, this is a row vector, so we write it as bra m. Then this is q operator and this is n. As the bracket is completed, so the integration over the space variable q is implied. This is a very shorthand notation for using this. Let me explain one more thing. As you have come to know that for hydrogenic electron, they can be represented by three quantum numbers n, l, m, and afterwards we shall see how the state is. We write this as a state as this. We are not considering the spin right now. If we write this one as n prime, l prime, m prime, NLM. When the bracket is closed, that means the integration over integration over r, theta and phi are implied. So with this introduction, let me first rewrite this equation. So let me rewrite this equation. So left hand side I have already explained, it is m q operator n, and on the right hand side we have, for this we rewrite this equation as q cap and q cap n is equal to 1 upon root 2 and similarly this equation is equivalent to ddq on n . So for this part, q n we write 1 upon root 2, 1 upon root 2, then n minus 1 ket plus n plus 1 ket n plus 1. 1 by root 2 is taken common outside, and then we have root n this is delta function. The same result as we have obtained earlier. Only thing is that we are to write less amount of quantities, and the most of the thing is implied. This is Dirac's bracket notation. We shall continue this to calculate the matrix element for q square, p square in the next lecture.